Chapter 8, Concepts of Chemical Bonding. There are three basic types of bonds. Ionic bonds are the electrostatic attraction between ions or between oppositely charged ions. This could be a metal cation and a nonmetal anion. It could be a metal cation and a polyatomic anion. It could be a polyatomic cation and a nonmetal, or it could be a polyatomic anion and a polyatomic cation together. Covalent bonding is the sharing of electrons. This specifically happens between nonmetals when they share their electrons. And metallic bonding involves metal atoms that are bonded to several other atoms. We usually call this an alloy. 8.2 Ionic bonding. The energetics of ionic bonding. As we saw in the last chapter, it takes 495 kilojoules per mole to remove electrons from sodium. This is the first ionization energy. We get 349 kilojoules per mole back by giving electrons to chlorine. This is the electron affinity of chlorine. These numbers do not explain why the reaction of sodium metal and chlorine gas to form sodium chloride is so exothermic.
We've asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. He can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. Now, the reaction between sodium metal and chlorine gas proceeds, but we know the ionization energy of sodium is greater than the energy released, the electron affinity, when chlorine accepts electrons. So the reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. The formation of that ionic bond, plus and minus charges attracted together, releases energy, and that's the driving force for this chemical reaction. And you can see that it's exothermic. Energy's being released. Bright red glow, typical of emissions from sodium. Now the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt. And Lonnie's prepared some in advance. He has white table salt, purified, that he can show us. There it is, purified in advance from Lonnie Laboratories. And Lonnie tells me the salt that he makes in Lonnie Laboratories is far superior to any salt that you can buy in the store. So what does he have to do now? Lonnie's going to demonstrate, clearly hasn't had his breakfast this morning, that Lonnie Lab salt far superior to any salt you could buy in the store. Thank you, Lonnie, for that demonstration that sodium chloride, an important spice and food flavoring. And when you make it yourself, the satisfaction is so much more complete.
There must be a third piece to the puzzle. We know that sodium loses an electron to form a cation, and chlorine gains an electron to form an anion. What is as yet unaccounted for is the electrostatic attraction between the newly formed sodium cation and chlorine or chloride anion. Lattice energy. The third piece of the puzzle is the lattice energy. The lattice energy is the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. The energy associated with electrostatic interactions is governed by Coulomb's law. Lattice energy then increases with the charge on the ions. So we can see that lithium fluoride, which has a +1, -1, has a lattice energy of 1,030 kilojoules per mole, whereas something like magnesium oxide, +2, -2, has a lattice energy of 3,795 kilojoules per mole. It also increases with decreasing size of ions. If we compare, well, let's look at lithium chloride and sodium chloride. Now, lithium chloride has a lattice energy of 834 kilojoules per mole, and sodium chloride 788 kilojoules per mole. So we can see that the lattice energy is increasing with decreasing size. We know that lithium is smaller than sodium. Without consulting your textbook, arrange the following ionic compounds in order of increasing lattice energy: sodium fluoride, cesium iodide, and calcium oxide. We know that sodium and fluorine are a +1 and a -1 ion. Cesium iodide consists of +1 cesium and -1 iodine. Calcium oxide is a +2 -2 situation. Because the product of the charges in Coulomb's law, Q1, Q2, appear in the numerator of the equation, the lattice energy will increase dramatically when the charges of the ions increase. Therefore, we can automatically expect that the lattice energy of calcium oxide will be the greatest of the three. Looking at sodium fluoride and cesium iodide, we know that the ionic charges are the same. As a result, the difference in their lattice energies will depend on the difference in the distance between the centers of the ions in their lattice, or in other words, because of their radius. Because ionic size increases as we go down a group in the periodic table, we know that cesium is larger than sodium, because cesium's at the bottom of the table, and also that iodine is larger than fluorine. Therefore, the distance between sodium and fluorine ions will be less than the distance between cesium and iodide ions, and therefore the resulting lattice energy of sodium fluoride should be greater than that of cesium iodide. And then in order of increasing energy, we have cesium iodide, sodium fluoride, and calcium oxide. Practice exercise. Which substance would you expect to have the greatest lattice energy? Magnesium fluoride, calcium fluoride, or zinc oxide? Sample exercise 8.2, charges on ions. Predict the ion generally formed by strontium, sulfur, and aluminum. Strontium is a metal in group 2A. It's an alkaline earth metal and will therefore form a cation. Its electron configuration is krypton 5s2, and we would expect that the 2 valence electrons can be lost easily to give a strontium +2 cation. Sulfur is a nonmetal in group 6A and will thus tend to form as an anion. Its electron configuration is neon 3s2, 3p4. It is 2 electrons short of a noble gas configuration. Thus, we expect that sulfur will form a sulfur -2 anion. Aluminum is in group 3A, and we expect it to have a +3 cation charge. You can also check these charges in your textbook in tables 2.4 and 2.5. Practice exercise. Predict the charges on the ions formed when magnesium reacts with nitrogen. Energetics of ionic bonding. By accounting for all 3 energies, that is the ionization energy or the energy needed to extract an electron from sodium, the electron affinity, that is the energy needed to add an electron to chlorine, and the lattice energy, that is the energy needed to break a sodium chloride lattice, we can get a good idea of the energetics involved in such a process. This is called the Born-Haber cycle, and I would like you to watch the accompanying videos on that. These phenomena also help explain the octet rule. Metals, for instance, tend to stop losing electrons once they attain a noble gas configuration, because energy would be expended that cannot be overcome by lattice energies. We can see from this equation that the math involved in the Born-Haber cycle can be summed up in this fashion. We have the enthalpy of formation, or the standard enthalpy of formation, is equal to the sum of the enthalpy of sublimation plus the enthalpy of bond energy plus the enthalpy of ionization energy plus the enthalpy of electron affinity plus the enthalpy of the lattice energy. Now these are the sum of all the steps in the Born-Haber cycle. So as you watch the accompanying videos, make sure that you're checking your math with this equation.